Hello dear students. In this class, let us learn the conservation of angular momentum. Conservation of angular momentum, and let us derive the law of conservation of angular momentum. Let V be the volume of an arbitrary set of material particles of a material body at time t. Okay. The angular momentum is also called the moment of momentum. It is defined as, let us take it as h naught, okay, equal to volume integral x cross rho v dv, where x is the position vector of any point in the material body, rho is density, and v, the arrow above, is the velocity, and capital V is the volume. Okay, guys. So, what is rho? Integral rho v dv. Rho v dv is nothing but momentum, right? Moment of momentum means you have to take this x cross. We have to take that x cross, where x is the position vector of any point in the material body. Okay, then we should take the torque, the applied torque on the material body. The moment about the origin of the total force is called torque. What is torque? Torque is nothing but moment about the total force. It's called torque, acting on the material body. So, how many forces are acting? There are two types of forces. One is body force. Okay, the other one is the surface force. Okay, and then I want what? I want the torque, that is x cross rho d and x cross s. Okay, for the body force it is volume integral, and for the surface force it is surface integral, and let us call that as G naught. Right? What is B? B is the body force per unit mass, and S is the surface force acting on the surface of the body. Right? Here surface must come. Let us write that on the surface. Okay, let us call that as equation 2. The law of angular momentum states that the law of angular momentum, the law of conservation, the word conservation is missing here, the law of conservation of angular momentum for a continuum states that the material time rate of change of the angular momentum is equal to the total applied torque about the origin. That is a law of conservation of angular momentum. Okay, so according to that, the LHS is d by dt of h naught equal to g naught. Right? Now we'll substitute for h naught. This is our h naught, and g naught is two integrals here. One is volume integral, the other one is the surface integral. Now we have d by dt on the LHS. Okay, by using Reynolds transport formula, this d by dt will go inside, and rho is the scalar here that is coming out here by Reynolds transport formula, that rho has come out. So d by dt of x cross v dv outside. The remaining on the RHS are the same. We'll keep them same. We'll change later. Okay, now what is d by dt of the product? We have the product x cross v, no? So first differential of the first term, the second one as it is, plus first one as it is, differential of the second one. dv equal to the same, the RHS remains the same. And what is my dx by dt? This dx by dt is nothing but the velocity. Okay, the rate of change of our x is nothing but the position vector, that is it is denoting the displacement, right? So rate of change of displacement is nothing but the velocity, is velocity here. So v cross V, and we know that any vector cross with itself is 0. So this part is gone, the 0 there. The remaining is what? Remaining, x cross dv by dt as it is, dv equal to same RHS. RHS is same. So we have the volume integral rho x cross dv by dt dv on the LHS equal to the RHS as it is. Okay. Now by using the Cauchy's law, so what is Cauchy's law? Cauchy's law states that S is nothing but the transpose of the stress tensor. So you can use either tilde here or arrow there. So you can use any one, right? Will not use the arrow, we'll use only tilde there, right? So T tilde transpose n cap. Okay. So now the place of S we are replacing by that, right? So S is nothing but what? S is nothing but T transpose n ds as it is. Okay, let us call that as equation 3. Let us call that as equation 3. We have an identity which says like this. The surface integral x cross a n ds is equal to, we are converting the surface integral to volume integral like this. Volume integral, right? To xi, where xi is the dual vector of the skew tensor of A. Xi is nothing but what? The dual vector of the skew tensor of A, right? Plus x cross divergence A. X cross divergence A. This x remains the same here, same x, right? And what is xi here? Xi is the dual vector of the skew tensor of A, right? Now look at equation 3. In the equation 3, we have the surface integral, that is this part there, right? The place of A, I have T transpose. The place of A, we have T transpose. Okay. So, xi will become what now? Xi is the dual vector of the skew tensor of A, and our A is what? Our A is nothing but T transpose. Our A is nothing but T transpose. So, xi equal to half, right, T transpose minus T transpose transpose. What is T transpose transpose? Itself, right, itself. So we are getting xi is equal to half T transpose minus T. Let us remember this xi. Okay. So now using this, equation 3 becomes, what is our equation 3? LHS. LHS is this. In the RHS, so in the place of the second, only the second integral is changing. Okay, remember the second integral. So LHS is same. Okay, LHS is same. This is our LHS equal to RHS. The first integral is same. In the second integral, we are putting what? We are putting 2 xi plus x cross divergence A. In the place of A is nothing but this T transpose. Okay, and dv as it is. So now we have, on the LHS we have the volume integral, on the RHS we have the volume integral, right? Two terms are the volume integrals. Now what we do is we'll take, this x cross things on the one side, right? Okay, on the LHS. So that implies on the LHS, the volume integral, we have rho x cross dv by dt, okay? Then on the RHS, right, this, will go that side, right, to the LHS is becoming minus x cross rho b. Then we have, this part is going that side, so it is becoming minus x cross divergence T transpose dv equal to, on the RHS, what is remaining? The remaining is this. The remaining is this. So that is equal to integral v 2 xi dv. Okay. Now in the next step, what do we do is we have everywhere, x cross, we'll take x cross outside. and there is a row, this row can be taken, this row will take here, right? So we have x cross rho dv by dt minus x cross rho b minus x cross divergence t transpose dv equal to the RHS there, right? So x cross is common, so we'll take x cross common, x cross the remaining all within one bracket dv equal to the RHS, right? Now from the Cauchy's equation of motion, we have rho dv by dt minus rho b minus divergence t transpose equal to 0, right? So what is happening now? This whole thing is gone now. It is becoming 0. So we have the RHS, that is volume integral 2 xi dv equal to 0, right? So when this can happen? It can happen only when the integrand xi equal to 0, and that is happening for all the volumes. Since our volume V is arbitrary, it has to happen for all the arbitrary volumes, so that xi integrand has to be equal to 0. And what is xi? Xi is nothing but half T transpose minus T transpose transpose equal to 0. And what is T transpose transpose? Is nothing but T itself. So T transpose equal to T. And what was our T? Our T was the stress tensor. T transpose equal to T. Therefore, the stress tensor is symmetric. This is the law of conservation of angular momentum. It states that what? It states that the stress tensor is symmetric. Okay, guys? So this completes the law of conservation of angular momentum. Okay, thank you.